Okay, so we're going to start with the 2015 test today. So we went in detail kind of with the 2006 one on Monday. We pretty much highlighted on chair confirmations because that was one thing that mostly everyone kind of was still kind of foreign with. They never really saw it before, so that was a good practice day for that. Today we're just going to go through it all and we're going to try to pick up the pace and try to go a little bit faster. So with nomenclature, what are your priorities that you have to go through in terms of starting? Right. What else?
Most branches. And then after that, like the number, the smallest number of the substituents.
Yes. So the thing is, the first thing is you want the longest chain possible, and at the same time doing that, you want the most substituents, and at the same time doing that, you want the substituents to have the smallest number. Okay. So which way would you start this? Which way would you not start this? That's a better question to ask.
Left to right.
So it's definitely not this, right? So you can't start from that side. Because if you did, your longest chain would be 1, 2, 3, 4, 5, 6, 7, 8, 9, but your first substituent will be on 4. Okay? If you started from here, you'd get 1, 2, 3, 4, 5, 6, 7, 8, 9, and you wouldn't have a substituent until number 3. So, so far this is better than this side, but we have to compare the top now, okay? So we get our first substituent on 3 here, but we get it on 2 here. 1, 2, and on 2 we have 2 substituents. These two, right? So 1, 2, 3, 4, 5, 6, 7, 8. That seems to be better than this way. But let's try the last way, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 was the highest amount of carbons that we could have had. And if you look, once we do number this, you notice that there's 2 substituents on 3, okay? So having seen that, you also see your next substituent on 4 and your next one on 7. Had we started counting from the other side, you'd get this. 1, 2, 3, 4, 5, 6, 7, 8. So your substituents would be on 2, 3, and 6, but you'd have a smaller chain going that way. That's why you know that the one in red is the correct way to go. Okay? All right. So where is my first substituent?
3.
And what's my parent going to be actually? Okay. So start with writing that. And then I always put a line underneath and then start writing the substituents under it. How many substituents are there on 3?
2.
And how do I note those down?
3 dimethyl. 3 dash dimethyl.
3 dimethyl.
3, 3. There you go.
Alright,
If
3,
you
3,
miss the number, you're not going to get the points.
Yeah, 3.
Okay? So 3, 3, dimethyl. What's next?
4. Is that
What is this?
Propyl?
Yes. And what's after that?
7 methyl.
7 what?
Ethyl.
Yes. And how do I determine what goes first? And what counts in alphabet?
Nick.
Yes. So Nick counts. N is for neo, I is for iso, C is for cyclo. So if you have any of these 3 letters before as a prefix with any type of substituent, those are the ones that count in the alphabet for being put in the order correctly. So what's going first on this?
7 ethyl.
Okay, next.
3 dimethyl.
Okay. And after that is the last one. We have 4 propyl. And what was the parent?
None.
Okay. So that's the first one. Any questions on that one? Okay. Next one, what's the parent for that?
Cyclohexane.
Good. And pretty much just remember, if you see a chair diagram, that equates to a cyclohexane ring, okay? So our parent is cyclohexane. And we can look at the numbering last, so I'll just put a number. So what is this group called?
Ethyl.
Okay, good. And you might not know what this group is just by looking at it. So what's a good thing to do in this case before we start doing it?
Line diagram.
Yeah, so if you do it in line angle, that's going to help you a lot. And once you're doing this, if you draw a squiggly line like this, it'll be easier to see what you're working with. So how many CH2s are there? Two, right? Okay, so here's the first CH2 and that's the second CH2, okay? And what is it all connected to?
Carbon.
And how many hydrogens on it?
1.
Okay, so if there's one hydrogen on it, that means there's two other groups on it, right? I think I am missing something.
So that's just gonna
Okay, yeah. So this is that carbon, and on that carbon, there's going to be a methyl group coming off of it. And so I'm just going to draw that H over here, like that, okay? Yeah. Now, to continue on, it says that it's connected to another carbon, which has another hydrogen on it. And that carbon is connected to how many methyls?
2.
Okay, so I'm going to erase the H's now so I can kind of see what's going on. I just drew them to see how I would look at it, okay? Let me draw this a little better. There we go. Does everybody see how we converted this to this? Does that make sense for everyone? Okay. So if we have this substituent coming off of it, what are we going to do? What's the first thing? We have to see which way is going to give us the longest number, right? So what is that number going to be?
4. 5. Yeah.
Oh, you,
So it's going to be 5. So what's the name of this parent substituent going to be? Yes. Okay. Now, where's the first number where we have a substituent on that? Substituent. Okay. So that means that this is going to be the number where it's on, right? We'll look at the number in just a second. So we know that it's going to start with parentheses. If you have a substituent and a substituent, you write the number the main substituent is on, which we'll get to in a second. And then you start where it is on the first spot. So 3, and then where's the next one? 4. Okay. And what group is on those two? So you're going to say dimethyl. And what is the main?
pencil.
Yes. So this is the substituent that's on there. And we end it with parentheses like that. And what was the parent? Well, we wrote that up here. So how am I going to determine which is going to go first and what the numbers are?
So the ethyl glycol will go first.
So yeah, you're going to be looking at this E and this M. Remember, only Nick counts, that's why we're not making it D. So your final answer, well, there's one more thing. What am I missing? Something about...
Numbers.
Yeah, that's right. I am missing the numbers. And we said that one's going to go first, right? So we already know that's going to be 1. Yeah. And this one?
2.
And why do I not go this way instead of down?
The substituent would be on a bigger number.
Exactly, because if you went this way and you said 2, 3, 4, 5, 6, your substituent numbers would be 1 and 6. Well, you want it to be the lowest number. So that's why you know if you only have one substituent left, you have to go this way. Okay?
Why don't you start with that ethyl?
So the reason you don't start with... Oh, no, you do. Sorry. You do start with that. My bad. Okay. So there's one more thing we're forgetting about cyclohexene chairs. What is it?
Trans.
Trans and cis.
Trans or cis. So that's what it is. So what is this one?
Trans.
Trans.
Why?
It's this. They're both equatorial.
But one's
That's
different.
wrong.
Oh, yeah.
That's exactly, that's pretty much
You right.
what makes people get confused. So don't look at how many equatorials and how many axials you have. You need to look at the orientation of how those positions are drawn. So in the question, she only drew one stick on each point. If we drew the other stick, it would be going up 180 degrees. And if we drew the other stick, it would be going down 180 degrees. And if you can see, on this point, equatorial's down, and on this point, equatorial's up. So if it's opposite, up, down, or down, up, it's trans. Yeah. So the final answer for this question is trans. One ethyl, 2, 3, 4, dimethyl, pentyl, and that's all in parentheses because it's a substituent. And then the parent is cyclohexane. Okay? And next one. So usually she also adds in a question on nomenclature where you have to draw the actual structure. So what's my first to-do item when you have that?
Look at the main thing.
Yes. So you're going to look at what your parent is. So what does this mean?
Cyclohexane. It means like a 5-ring.
Yeah, so it's going to be a closed ring and there's going to be 5 carbons in it. So it's going to be in the shape of a pentagon. I'll do this right here since I got some empty space. So I'm going to draw a 4-membered ring. Okay? So it says on it it's a trans group and there's 2 substituents on it. The first one is 1 isopentyl. So where do I put it?
Anywhere.
Anyway.
Are you sure?
Yeah, as long as your other.
Yeah, so there's nothing on it and we're starting it, so it doesn't matter where we started from. Okay? So I'll just start it from here, okay? And it says it's supposed to be trans, so I'll put my first one as a
You
wedge.
can use any type, right? You can do the...
You can do wedge or dash
Okay.
because it's trans. You have to make sure the 2 are different. Okay? So what does isopentyl look like?
Big 2 like you draw this line and then don't a carbon like goes this way.
So yeah,
It's like
just
splits into 2.
draw a fork like that. So right now we have 3 carbons so far. Now we have 4. Now we got 5. So 1, 2, 3, 4, 5. That's what isopentyl looks like. Okay, guys?
Oh, you have to draw the fork at the pen.
Mm-hmm. That's what isopentyl is.
Then you have 1 extra bond. Or, never mind.
No, I don't. So 1, 2, 3, 4, 5. If you ever see the word iso, just equate it to this and just factor it in your mind, okay? Iso means it's coming off an isolated carbon. It's coming off 1 carbon, and there's 2 forking out like that. That's what iso is, okay? So the next one, it's a compound substituent like this. Oh no, that's where it is. Sorry, like this. Like this one that we just did. Like there's one substituent, and within it, there's another substituent. So what is the quote-unquote parent substituent?
Beautiful.
Okay, so where do I put it?
You can put it on the
Bottom right or
left.
bottom left?
Okay, and why is that?
Because it has to be 3 and you can do
Because
that.
there's 1 carbon in between both sides, and it will be identical if you put it here or if you put it here. Okay? And do I put it on a wedge or a dash?
Dash.
Dash.
Okay. Good. And so the parent substituent we said was what?
Beautiful.
So 1, 2, 3, 4. And where are my subs coming off from?
2.
Okay. And what are they?
2 methyl.
2 methyls, okay? Is that it?
Yeah.
All right, so the important thing about this is to note what the parent is, which we did. We drew the pentane. Then the next thing is to see the orientation of how the substituents are. We saw it was trans, so we knew that one is going to be a wedge and another is going to be dash. And we saw the isopentyl. We said it looks like that. And this was good practice for a substituent on a substituent. So we're done with nomenclature. Does anybody have any questions on that so far?
How would this be? Would it be 2 wedges?
Say that again?
How would
Two
this
wedges or
be?
two
Cis could be 2 wedges or 2 dashes. They're identical. Your test could have 2 wedges, yours could have 2 dashes, and y'all will both get the points for it. All right, next question. This is beginning facts. This is saying to rank these compounds in increasing boiling point. So what do we need to know for boiling point to answer this question?
Number of substitutes.
Yeah, exactly. So all y'all are right. So if you have branching and you have a lot of it, what does that mean for boiling point?
It goes down.
So they're inversely related, right? This means low boiling point. So if I see a structure with a lot of branches, which one would that be? Yes. So that one would be what number? Yeah. Okay. And which number, which one would have the highest amount of a boiling point?
I don't know.
And why is that?
Only has these branches.
Yes. And the next one is 2. Again, a lot of people try to be smart with it and be like, let me just put all 2, let me just put all 3, let me just put all 1 so I can get 1 point. She'll give you 0 points for that. So definitely do not do that. Okay, and if boiling point decreases with increasing branching, what does that mean for melting point?
Opposite of that. Indeed.
Yeah, so just know increased branching equals increased melting point. Okay? So on to the next one. How do you calculate formal charge?
Line of valence minus lines plus dots.
Yes, so valence number minus sticks and dots. That's what that is. Okay, so what is carbon's valence number? How do you know what the valence number is?
Look at the
Check
periodic
on the
table.
periodic table. Whatever the column is for that element, that's the valence number for it. Okay. So what am I going to subtract this number by? 4 minus what?
4 minus 4.
Yeah. So sticks and dots, right? We're going to count the sticks and dots. So this is 1, 2, 3, 4. So this formal charge is
0.
good. All right. What's nitrogen's formal charge? Valence number.
5.
Okay. Then you look at that on the periodic table.
Increasing branches.
And what am I going to subtract it with?
4.
Okay. And, 1, 2, 3, 4. So 5 minus 4, what's the formal charge?
1.
Okay.
So she mark off if you don't say +1?
No, she won't. Just make sure it's not negative 1. Then you'll get it all.
You don't look at the branches on the other side, the carbon?
What's that? No, the
okay,
question
for
had
nitrogen.
an arrow on nitrogen with a box under it, asking the formal charge specifically for that. Okay? Okay, so we're done with that. What's next? What's next? All right, the next one, she gives you a structure, and she's gonna say to give the different amounts of structural isomers. So for monobromination, how many bromines are we gonna add on it? All right, cool. So I'm gonna leave this here. I'm not gonna touch this. I'm just gonna draw it again. Guys, if you have questions, please stop me. Okay? Please stop me if you have questions. So where should I put it first? Where do you want me to put it first?
One of the forks.
Tell me which one to put on.
It doesn't matter.
Top right. But you just have to make sure it's not the
Top right.
same, like since
Okay, we'll put it on the top right. So if I were to put it here, would it have been different?
No.
Here?
No.
Here? Okay, so that's how we know we're done with these points. Because if we were to have put this bromine on either one of these other sides, it would have been an identical compound. And structural isomers are not supposed to be identical. They're supposed to be unique. Okay? So where else can I put it?
On
The one next to
the
it.
one right, like below it. You see?
Look right here?
Yeah.
Okay, so let's draw it again.
Okay, are you guys?
You close the door just a little bit, not all the way. Yeah, that's the one. Okay, so you said over here, right? So can I put it only there?
No, then the one right next to it.
Okay, so I'll put it right next to it, right?
No, not that one.
Alright, which one do you want me to put it on?
It doesn't matter which one, as long as either one.
Exactly, I can put it on any of these. All of these are identical. Okay? So you have to look at it and see, if you put it here, how would it compare if you put it on the direct opposite side?
Would you like number the carbons? I mean, like letter them so that you know.
That is a great way to do it. I only do it if the structure is a little complicated. Oh, is that what you're laughing at? But this is a very symmetrical structure. There will be structures where like if you had a structure like this, putting stuff in different places would be different because this is a very unique side on this structure. But the fact that this structure with itself is absolutely symmetrical, I didn't really draw the letters, but I can. So A, and where's B?
Right, now.
Okay, so B, I'm sorry, that's cool. B, and where's C?
Where the host is.
Good. So that's a really good way to do that. So you know what's unique and what's not. Okay? So having done that, you kind of should know where the third spot should be for this, right? And again, it doesn't matter which direction you put it on, they're all correct because they're all unique. Does anybody have any questions
I
on
have a
this?
question about cis and trans. When do you use those?
Well, this has nothing to do with nomenclature.
No. So like whenever we were doing some of the practice tests, they would show like geometric structures, like the same thing, like romanation or chlorination,
Okay.
and they would show cis and trans to where
It's
one
going to
is
tell
off.
you in the question to use.
To circle them out?
No. It's going to say, well, yeah, I don't say that, but it's going to say show all the structural and geometric.
Okay.
Geometric stands for 3D orientation, which means cis and trans, wedge and dash. This question strictly only asks for structural. So that's how you know you have to draw all the structures that wouldn't have stereochemistry. Stereochemistry meaning dashes and wedges and cis and trans.
So for this one, let's say it's a geometrical, would you be able to do it? So what, like, how would it?
You could put a wedge on like one of the arms and then a dash on the other, and then.
Yeah, you could, but since it didn't say to, you don't have to worry about that. Okay, next question. So this is a very easy question, and
Question like this.
you probably will.
It's like super light.
You probably will, honestly. Actually, I took this test. Yeah. Okay, so a good way to check for polarity is you should just draw the structure, even though you're not required to on the test. So we have our carbon. It's bonded to 4 domains, 2 H's and 2 bromines. So which one of these are really electronegative compared to the others? Okay, so that means bromine is going to be having a strong pull on it, right? Is there any lone pairs on the carbon? Okay, good. So that means we can check if the carbon was a truck in the mud and we had 2 poles that were really small and we had 2 poles that were really strong, would the truck move?
Yeah.
Okay, so the truck would move this way, right? So if the truck's going to move, what does that mean?
It's polar.
Yeah. So we know that this structure is going to be polar. Okay? If you're following along, try your best to also write what I'm writing because it's really going to help with all the other things. Okay, so the next one, we have a carbon and there's 2 oxygens. And we know it's going to be double bonded because carbon's supposed to have 4 bonds on it, right? So which one of these are really electronegative compared to the others? Okay, so oxygen is going to be the one doing all of the pulling. And are there any lone pairs on the carbon? Okay, so that means we can use that truck example here too. If carbon is the truck and there's two identical forces being pulled on each side, is the truck gonna move?
No.
So what does that mean?
Not polar.
Also, I wrote NP, but the test might say N. So make sure to write what it says. Don't write NP if it says to write N for non-polar, because she won't give you the points for it. Did it say N on the test or NP?
And
All right, so we'll just take it.
What if the carbon had a lone pair?
If the carbon had a lone pair, then it wouldn't be pulling equally. There would be like a hindrance with the amount of force being pulled on both sides, and it wouldn't be the same.
So
Can
there'd
we
be
do
slight
like-
polarity.
So it'd be polar.
It does affect polarity.
So can we do something like NH3?
We did that on the last exam for sure.
There's two.
Okay, does anybody have any questions on all of what we covered so far? If you guys do have questions, please ask.
Yeah.
And try to also write down what I'm writing. It's really, really going to help you a lot.
So what does a lone pair do?
It acts as a source of electronegative density.
So it acts like this pulling.
Zach, can you push the button on the camera? And just turn it off. Just turn it off. Was it recording?
That is.
Okay, just push the red button on the top. All right. So to continue on, we're starting with the question where it's asking us to rank the indicated hydrogens in increasing acidity. And the structure that we have for that question is this. And definitely ride along with me. It's going to help you the most if you ride along with me so you can kind of know what's going on. And it's going to also be a good thing to refer back to once you're working on tests on your own. All right. So this is the structure that we have on the question. And the way to answer this is you're going to have to look at the poles and the possible resonance that's in that pole and everything else in between. So if you look at this structure, well, let's label the hydrogens first. So it's this one, the middle one, and then this one. So we're going to rank these particular spots. Okay? Does anybody have a guess as to which one would be the least acidic?
The right one?
Why is that?
Because it's the farthest away from the oxygen.
Okay, so we'll write one over here and come back to it. What about the last two?
The left one. Yeah, and then the left one, the second one.
Okay, so y'all are right. And does anybody want to explain why?
The closer you are to oxygen, the higher acidity.
Yeah, so if you can see, oxygen is a really electronegative atom, and it's the most electronegative one in this complete structure, right? Because the rest is just carbon and hydrogens. So there's going to be particular mechanisms that y'all will use that will enable you to begin a resonance structure with these that have a carbon double bonded to an oxygen. Y'all haven't learned it yet, but it's a good indication that resonance will happen in that particular location. Since y'all haven't learned that, y'all can do it like this, okay? The gigantic pulling factor is going to happen on these oxygens, right? We know that for sure. Okay? So if that's where the majority of the pulling is going to be, that means that the hydrogens closer to that point, closer to those points, are going to be the ones that are going to be highly acidic. Okay? So because the hydrogen over here is in between both of those particular spots that we just talked about, is going to indicate that it's going to be the highest in the acidity trend. Over here, we have the hydrogen that's close in proximity to one oxygen, for which is why we know that it'll be next. In this one, there is a pull of an oxygen on it, but it's in between a carbon. This carbon is hindering it from being able to interact directly as those two are. That's why we know this is going to be the least acidic. She could have asked you this same question and said, rank the following in increasing basicity. So pretty much 2 would be the same, these would be flipped. So with basicity would be opposite. So just really take some time to read the instructions or the directions so you know what and how to answer. Does anybody have any questions on this one? Okay, moving on. The next one is, this is what you were asking about, the base and the acid question. So let's go ahead and write this one. Does anybody know what this OC group that's like this, connected with a double bond, does anybody know what it's called? She may have barely used the name, but if you don't know, that's fine.
Aldehyde?
No, this, I'll tell you. This group right over here, I'm just talking about the carbon and the oxygen. This group is called a carbonyl. It's good to just kind of factor that into your mind. We'll be talking more about this in the coming exams. Okay, so with these questions, you're going to have 2 structures given to you. And your first job is to indicate what is the acid and what is the base. So knowing what you know about acidity and basicity and what we went over the weeks leading up to this exam week, what is what and how do you know it? So like this. What is this, the acid or the base?
Acid.
Okay, I'll write that. And the next one is obviously the base now, right? And you kind of know already that NOH is a base because it's one of the strong bases that you have to memorize in general chemistry. Okay, so what do acids do?
They donate electrons.
Yeah, so they're the donators of H's. They donate H's, and what do bases do? Exactly, so we're going to accept H's over here. So if we know that this acid is going to be losing the hydrogen, we can already draw that figure in here. Okay? And the cation or the proton source from the other side will now translate onto the side that lost that H+. Okay? So over here we can just write Na+. Okay? And if the Na+ is here, then what does this structure now become?
H2O.
Exactly, so it's just going to be water. Okay, so what is this compared to that?
Weaker acid.
Yeah, it's a weaker acid
It's a
or
conjugate base.
conjugate, yeah. And then this one?
Conjugate acid.
Yeah. Now, how do we determine the direction of the equilibrium? How do we know which way it goes?
It goes to the weaker.
Yes. So, a good way to compare it is just look at the acid and look at the base that you wrote, okay? Over here we have this group. And what do we know about S, sulfur?
Very electronegative.
Yes.
Less so than oxygen.
It's bigger than.
But
It's
it's
big.
bigger than oxygen, right?
Yeah.
If you look in the column for 6, the group 6, and you go down, size is what matters because you're looking in the same column as oxygen. So like this is just a side note. This compared to this, which one's more acidic? This group with the OH or this group with the SH?
That's it.
Because of what?
It's a little bigger.
Yeah, because of size, exactly. So that was just a little side note, but if we know that this is a pretty strong acid, this is like a very strong acid, then this lacking that H is going to be a weaker acid. So this is weaker. And then this we know is a very strong base. And water is a very weak acid. It's not a strong acid. So this is also weaker. So you just have to compare them and see which way the direction is going to go. And you can obviously tell it's going to lie to the right. Any questions on what we did so far? Yeah, no problem. So let's compare the NOH into H2O. You understand how NOH changed to H2O, right?
Like
Sometimes.
Start over?
Yeah.
Okay, yeah, no problem. So, okay.
Would we write that NA plus in the box for it?
Yes, you do.
Just like smaller?
Yeah, because it's floating in the environment.
Like sometimes when it's not like NaOH or something obvious, like how can you tell that it's like the acid or base? Because I get confused.
One second, I'll help you with that.
Yeah, can you do another problem?
Yeah, we can look at the one we did from 2006, or we can do another one. But let's finish this test first. Okay, let's finish this test first, and then we'll do it. I'll start again for y'all.
Well, I mean, we can start again if you want.
The other one? Yeah, we'll just do that. So you want to start again from the next question? Yeah, we'll do that. Is that what you're saying?
Yeah, we'll just wait for the, for sure.
Or did y'all want me to go over this again? I can go over this
No, we're saying
again.
that you can like
No.
keep on going with the test and like
Okay.
complete test.
Okay, cool. We'll come back to this question. Just remind me and we'll go over it again, okay? Pretty much what you're doing is you have two structures, right? And you have to look at it and see which one is the acid and which one is the base. After you determine that, you do what an acid does, and then you do what a base does. And then you carry it on from there. We'll look at another example, don't worry.
I think the hardest part of that question is like trying to figure out which one's strong, which one's weak.
Mm-hmm. I feel you. How are y'all with resonance now? Okay? All right, so let's do this question. There we go. All right. So what do I have on this structure? What kind of charge?
A carbonyl ion,
Yes. And what do we know about carbon ions?
very unstable.
Yes. So which way is the bond pushing and electron pushing going to happen? Is it going to go towards it or away from it? Away. A good way to know that is what does a minus charge mean on a carbon? Or on anything?
Overly satisfied.
Yeah, so it has too much stuff on it, right? So if it has too much stuff on it, that means that you want to get, oh, I should not be showing this. There we go. So if we have a anion on it, it has too many bonds on it, so that's why we move it away from it, okay? Now, which way am I supposed to move it?
So the left,
Right.
Pretty much I'm supposed to move it on both because there's an adjacent double bond on both sides. So it doesn't matter which one I do first, so we'll just do it. So I usually circle the lone pairs, and I'm going to show an arrow going this way to indicate the resonance being able to happen from this side, and then likewise on the other direction. And you can also letter the particular direction you're going from, okay? So what's important with resonance with your arrows? What do you have to make sure?
The resonance.
Yeah, they have to be double-sided arrows. If you don't make double-sided arrows, you won't get the points for the question. So that's really, really important. All right, so I'm gonna go with A first and do that, okay? So if I move these lone pairs to this bond over here, what's gonna happen?
The
It's
carbon
gonna move the
replaces-
double bond to the.
Exactly. It's gonna move this double bond here, which in turn will do what?
Move the oxygen double bond to.
Exactly. Okay, so we moved once, and it moved everything in its path. So you have to really be careful and look at what is being moved and what you're starting with. If you have lone pairs and you're using resonance, they go to a double bond. If you're starting like that, you just have to remember that. And then if you're going from this to something else, you're going to go from that to lone pairs. So we had lone pairs, It's going to go here, so now it's going to become a double bond. Okay? And this bond over here will now become lone pairs. Okay? I actually got ahead of myself. Like I said, if you're starting with lone pairs, they go to a double bond. And if you have a double bond, they go to lone pairs. Does that make sense? Okay? So, this stays where it was. What's next?
What about that other radical that you moved in the lone pair there?
This one, right?
The other one.
We're going to come back to that after we completely finish this side. So what am I going to do with this?
You're gonna move that to the left?
Yeah. So now this will come onto this bond and become what?
Double bond.
And then this?
Oxygen will become
Lone pairs.
lone pairs.
Exactly. Am I done with that? If I move lone pairs back on here, will it change anything on this side?
No.
No, right? So we know that we're done with that. So now we can continue on with the B direction of the movements, okay? I'm gonna do this like this, okay? So if I move this up here, this lone pair will now become what?
Double bond.
Yep.
Then the double bond connecting in HN will go to nitrogen.
Mm-hmm. Exactly. Now, can I go further in this? If I move this back here, will it change anything on this side? Will it? If I use these lone pairs and I bring them back here, will it change anything on this side? No, right? So we know we're done. Now, the question is which one of them is the major contributor? Does anybody know how to figure that out?
First off is the octet rule.
Yeah?
So
After that.
there'll be two, right?
There's only one major contributor all the
Wouldn't it be
time.
the negative charge on the oxygen? You would
Yeah.
always get oxygen.
Why?
Because the oxygen
It's
is
the most
electrical
electronegative.
Yeah, so it goes back to basic general chemistry, which y'all know. CNOF, you're going in the order of the periodic table, and you're comparing N and O. O is more electronegative, hence that is your major contributor.
Wait, how do you know when you're done, Ken?
What's up?
How do you know when you're done?
Well, you know that you're done because over here, we moved this double bond and made them lone pairs here, right? Now, if you brought this back and did it to move this bond, it would just go back to where it originally was as a lone pair, right? So drawing a repeat structure doesn't make any sense because you already have it, right? If you were to bring it down here, as you can see, there's no double bonds on the adjacent carbons next to that double bond, showing you that there's nothing else to do in your path for continuing on resonance structures.
Okay.
All right? Does anybody have any questions on this so far? Any other questions on this one?
You could keep moving the other bond.
This one?
Yeah, you could keep the other one to the right.
This one?
Or right. Up. Yeah, you could keep moving that, but it would be a super minor contributor, right? So you don't draw it.
Well, we already moved those.
But it would be a different structure than the other one because now there's a lone pair of nitrogen.
Okay, so you're saying if I move this back
No.
over here,
No,
it's
no.
going to move this? That's what you're saying?
No, no. If you move the bond on the right to the.
But
as a
where
lone-
would you move it?
To the other carbon.
This
Like
one? You're saying to move this here?
No, no.
This here?
The bond to the right, move it up.
The bond to the right here?
Right. Go right again. Go right again. That bond, move it up as a lone pair.
How can you move it? There's no sign. You can only move stuff if there's a carbocation or a carbanion next to it.
Okay.
Yeah, so that's the point. That's like a really important point with resonance. You can only have resonance if you have a carbanion or a carbocation. Right. Any questions on this one? All right. All right, next one. So this is just saying to write the hybridization of the indicated carbons. If y'all have questions, please don't be afraid to ask. I want y'all to ask questions. All right, so the carbons indicated to show the hybridization for this one. And this one. And the last one is right here. So when you're doing hybridization questions, what's really, really important to look for?
Resonance.
Yes. Do we have any resonance over here?
No.
Okay, so what's the domain? What's the hybridization of this carbon that's indicated?
SP.
All right. And how did you know that?
Triple bonds count as one. and then-
Yes. So SP correlates to two domains. Okay? And those two domains you can remember as SP is S1, P1. 1 plus 1 is 2. Okay? Here's that first domain. Here's that second domain. The triple bonds count as one domain. Okay? Next one. Do we have any resonance on this one?
No.
No, right? And how many domains are on this carbon?
4.
Good. So this is that first domain. That first hydrogen is the second domain. And that second hydrogen is the third. And then this carbon is bonded to that carbon, making it the fourth domain for why this is sp3. Alrighty. And what about the next one? Do we have resonance on that one?
Yes.
So what are we supposed to do?
You can move the lone pair to the other carbon as a double bond. It would be sp2.
Exactly. So Adil, what are we supposed to do with carbanions?
You're supposed to move the lone. You're gonna move the lone pair to the carbon.
Yeah, you're supposed to move it to the carbon because it has too many bonds.
Yeah.
So you have to satisfy it by taking that domain off of the carbon.
Something else like I was
Mhm.
told is that if you have like a minus, then that means you're supposed to move it like away from the sign.
Exactly.
And
Yeah.
then if you have a positive, it's like towards.
Yeah, we went over that in the review days. That's a really good point. Plus is towards, minus is away. And if you think about it chemistry-wise, minus means too much, so you want to take it off. Plus means not enough, so you want to take it towards it to satisfy it. So what's the domain going to be now?
sp2.
Yeah. So this, having gone through that formation, will look something like this, right? C double bonded with the C and then H2. So that's that first domain. First hydrogen is second, and the second hydrogen is third. So this is sp2. Okay? Next question. It's saying what is the CA, CV, CC bond angle? So how do we know which of these carbons we have to look for mainly to determine what that hybridization is going to be?
B.
At the top, there's a.
Yeah.
Oh yeah, you're right. I missed that one. Thanks. So what's the domain for that?
sp2 moves the resonance.
Yeah, so this pair of lone pairs counts as 1, this one counts as 2, and then this one counts as 3. 3 domains, sp2. Thanks. All right, so which of these carbons do we look at for the bond angle? So it depends on the intermediate one. So CB is labeled as the one in between the two that we just did, which is right here. So first off, let's see what the hybridization of that one is. So what is it?
So SP3?
Yeah, because why? Because there's 4 domains around it, right? So this is a sp3 carbon. And does anybody remember what the sp3 carbon or sp3 hybridization bond angle is?
109.
Yes. Because all tetrahedral structures have a bond angle of 109.5. What's the most famous tetrahedral structure?
Methane.
Water.
Pyramids of Giza?
Well, water. The water is like a really basic like thing that we've learned how. Yeah. So. I was like, what? The pyramids of Giza?
You guys are not on the same wavelength, bro.
Huh?
You guys are not on the same wavelength.
Yeah. Okay. So the next question says that the sigma bond. What's a sigma bond? Do y'all know?
Single bond.
Yeah. So sigma bonds means single. And what do pi bonds mean?
Double.
Pretty much not single. It could be anything. Or it could be a combination of multiple singles. Yeah, so the sigma bonds between the between the atoms labeled as A, which is this one, and the carbon labeled as B, which is this one. It's saying to show what the overlap it is between those orbitals. So how are you supposed to answer this question?
You look at the hybridization of Ca, and then you look at the hybridization of Cb, and then you just list them.
Yes, that's exactly what you do. So what's the hybridization of Ca?
Sp.
Yep. Because there's there's 2 domains, so that's Sp. And what's the other one?
Sp3.
Yeah, because there's 1, 2 hydrogens, 3, 4. There you go.
Wait, sorry, can you do that one more time?
No problem. So Ca, how many domains does Ca have?
2, 2.
Yeah, because the triple bonds count as 1, and the single bond counts as another one. And S1P1 has 2 domains. And the next one, which is carbon Cb, how many domains does this have? Yeah, so 1 domain here, 2 domains bonded to the oxygen, and then there's 2 hydrogens bonded onto the carbon. So there's 4 domains for S1P3.
So that's the answer, SP? And
Yeah, that's how you answer this one.
Wait, so on the test, yeah.
Yeah, what's up?
Okay, never mind.
No, I'm listening, what's up?
No. It's on the board.
All right. You sure?
Yeah.
All right. So on the test, it's good for writing overlap to write the overlap like this, to show that these are the 2 that are in question. You just write like a little dash in between it. That's probably the best way to do that. Okay?
To write it that way, like in the answer.
Yeah. All right. Let's see. So what do we have left for the test? That, if y'all could just remember, there's like 2 things.
Neighborhood projections
And
and
Check confirmation.
yeah,
mechanisms.
And initiation.
The mechanisms.
yeah. All right. Can I erase all this?
Let's try.
All right. So let's do this one. So we're gonna start with the Newman projection problem, continuing on with the 2015 test. All right. The question is asking for viewing the molecule from the carbon-3, carbon-4 bond. Okay. So which way am I going to number this?
Aren't you missing the?
Does it matter which way I number it?
Aren't you missing one methyl on the third?
Am I?
Yeah, you're gonna think of
Yeah, my bad. I am. If you notice, it doesn't matter where you number it from because they're all encompassing of a methyl group in between each point. If you notice that. So if I numbered it from that side or the other side, it's the same thing. Okay? So I'm going to go ahead and number it from this side because it's closer to me. Okay? Actually, I'll probably just end at 4 because the question is asking for the carbon-3, carbon-4 viewing bonding, okay? So I'm going to draw an eyeball, okay? All right. The last part of the test is the mechanistic part of the test, and so let's go ahead and do that one. We're almost done, guys. Almost done. All right. So we have a CH3, a nitrogen, CH3, CH2, connected to a bromine. Okay. Is going to a CH3 plus and CH2, CH3 next to a CH3. This also has a H plus bromine minus going to CH2CH3 and plus a final HBr. So this is all going in one gigantic sequence. You're going from here, then from there you're going to go here, and then the reaction ends like that, okay? So your job is to see what you start with and then to see how you end with what you have. So if you start over here, you notice that you have this nitrogen connected with these two methyls, and then you have this ethyl connected to a bromine. And what you're supposed to do is compare this directly next to what it's reacting into, okay? So if you look at this, you see that the bromine is connected to this group. And then over here, that bromine is now detached from that group. And on top of this is this group that was connected to the bromine connecting onto that nitrogen. So somehow there's going to be some bond pushing and electrons causing that bond pushing to make this bromine go away. So given these lone pairs on the nitrogen, what would you guess happened for that bromine to go away from that CH3CH2 group?
Initiation.
So in this question, it's saying for the reactions below, provide the curved arrows. Why am I showing you all the answers? Hold on. All right. So the question is saying, for the reactions below, show the associated mechanistic bond breaking and bond forming. So in this question, she wants you to draw the arrows correctly going from one molecule going on to another molecule for allowing the bond breaking and the bond forming to happen. Okay? So she's not necessarily asking you, show me initiation, show me propagation, or show me termination, which she did on all the tests except for this one. And it's possible y'all's test might not have it either because of Harvey, and she said on Thursday she'll tell you if it is, right? So if it isn't, she'll give you maybe some kind of mechanistic question like this, okay? So the important thing with this is to know that the lone pairs over here are going to come onto this carbon that's connected to that bromine, okay? You have to show that. And having shown that, you're going to then show that with that mechanistic bond, with that mechanistic arrow attacking that carbon with the bromine will leave that carbon. So you show an arrow going upon itself like that. So what we're showing is something's attacking that group with the bromine on it, because we see over here that the bromine has now left that group. Because in the question, it has a plus sign in between both, showing that bromine is by itself. It's isolated. This is the way that you show that bromine going through that process. Okay? Pretty much what happens after that is you're now, after having shown those arrows on this part now, and now you have to compare this with this. Just like how we compared this with this. Okay? So over here, we see that this bromine that was isolated has now become an HBr, okay? So that means that somewhere on this structure is going to be an H, which will leave from this structure and come and combine onto the bromine, okay? And as you can see, nothing else will be added to this structure because the only difference between this and this is the lack of this hydrogen. So when you get these questions, don't get overwhelmed with, oh man, which way do I show the arrow? What you need to focus on is look at what you have and look at what you have to change it to. If you see that, then you'll never miss these, because you'll see that there's something in the starting position reactant that needs to go away, and there's something that needs to appear. So you need to pay close attention to what those two things are. So if you look at the next one, you see that. And what you're going to do is this bromine is going to have its lone pairs come and attack that bond with the hydrogen. Okay? And what did we show to show something coming off of it? You put an arrow upon itself, just like how we did over here, an arrow upon itself to show that it's detaching from that group. Okay? So yeah, once we show that, this H will come and combine with the bromine, and this group will be left as is.
Wait, I don't know if that's supposed to, like over there. The one that's supposed to be up, but like, there's an arrow pointing down to the nitrogen.
Yeah.
Yeah, that's actually the right way to do it. I apologize. Sorry. Okay. Next, we have this. What is this group called again?
Carboxyl.
Yeah.
Carbon.
This actually is called a carbonyl.
Oh wait, it's an OH.
And plus CH3, NH2, and this is going to CH3CH, and O, and CH3NH2. Okay, so like with the rest of the stuff that we've been seeing in this question, We're going to look at what we have, and we're going to look at what we want. Okay. Over here we have double bonded oxygen with a carbon, and over here that same bond becomes a single bond now. And as you can see, this group, which is isolated from this group on the left, now attaches onto that same group. Okay, so you haven't learned this yet, but most of the time when you have a carbonyl, what happens always, there's a reaction called the Grignard reaction, which you're going to learn in the second and third test, where you have lone pairs that come and attack this carbon on that carbonyl carbon. Okay? Once this happens, you have that bond, you have this lone pair coming and attacking that carbon on the carbonyl, which causes this double bond to go up and become lone pairs, like that. Okay? Hence why you have an extra set of lone pairs on this top one, which is shown on the question. Okay? So that's how that one works. And once you do that, this entire group, which was isolated, now comes and combines onto that same carbon, which is what happened right here. Does that make sense? So you're attacking and then combining what that group was that you attacked it with. You did the same thing over here too. You had this CH2CH3, which somehow came and did an arrow pushing attack, which caused it to attach onto that group. And the same thing here, you have that nitrogen lone pair coming here, attacking, and then adding on that group onto it. So you're looking at what you got, and you're looking at what you have to change it to. Is there any questions on this one? I know this is kind of like different from what y'all have seen so far, but the more exams you do, the more easier it'll be to understand in terms of what to do when you have different types of questions. This is the last question and we're done. Okay. Again, this chart will be given to you on your exam. Okay. And let's refer to this. Okay. On the question, you have... Huh? Are you sure?
We gotta test it.
So no bond energy. That means you will have termination, initiation,
Yeah.
and propagation, probably.
We hit that.
So you're sure she said no bond dissociation energy question?
She said it.
Okay, if she said it, then I don't have to go over this. But I did go over it in the 2006 test. So it's a good idea to just look at it and kind of understand what's happening. Basically, I'm just going to write the formula down so you can use it if you do the question. It's BDE, it's broken, minus BDE formed. And that's how you do that question. Again, I went over this in the 2006 exam. It's actually pretty straightforward. You're just applying numbers and adding and subtracting them. That's all you're doing.
What was the answer for this one?
The answer for this one is negative 16 kilocalories per mole. And the equilibrium is favored for the products.